Hello and welcome dear student in the next video lecture or the module of the topic solid state. So dear student, in the last lecture we have done the packing efficiency. What is meant by packing efficiency? Packing efficiency is the volume of the particle for the unit cell occupied with the total volume of the unit cell into 100. So, in that we have calculated the packing efficiency for the simple cubic unit cell. And as we know, for the simple cubic unit cell, the number of particles are n. N means which number of particles and which is equal to 1. And therefore, when the simple cubic unit cell are formed, then the space occupied by one sphere, that means one particle, which is equal to 52.36%, and a void present in the simple cubic unit cell, which is equal to 47.64%. For the BCC, we have calculated the packing efficiency for the BCC, means the body centered cubic unit cell, and in the BCC, N means the number of particles, which is equal to 2, and therefore the space occupied by the two particles, means the two spheres, which is equal to 68%, and the void present in the BCC type of a crystal structure, which is equal to 32%. For the FCC, we have not done the calculation for the FCC, means the face centered cubic unit cell, but for the FCC, just like SC and the BCC, the FCC or in the FCC, the space occupied by 4 particles, because for the FCC n equal to 4, that means the number of particles involved, which is equal to 4, and therefore the space occupied by the 4 particles, which is equal to 74%, and how much void space is present in that FCC is equal to 26%. So from these we have a crystal structure which is a more closely compactly packed. The face centered cubic structure is very much closely packed by the particles, because the space occupied is more and the void is less. Out of these 3 structures of the cubic unit cell, simple cubic unit cell, body centered cubic unit cell, and the face centered cubic unit cell, the face centered cubic unit cell, in that the particles, when the crystal structures are formed, they are very closely compactly packed. So dear student, this much part we have done in our last lecture. So today we start with a new and a very interesting point from the solid state topic called as defects, or it is called as crystal defects, or it is also called as imperfections. Crystal defects or imperfections. So in this module we are going to study first what is meant by defects, then what are the types of defects, and then in that vacancy defects, self-interstitial defects, Schottky defects, and Frankel defects. So that part we are going to study in today's module. So first of all, what is meant by defects? As we know, real crystal are never perfect. When the crystallization process occurs, then really no crystal is a perfect crystal. That means there is some faulty or the imperfection in that crystal, it will be occurs. That means really no crystal is a perfect crystal. They contain some fault or the imperfection in that crystal structure when the crystalline solids are formed, and that imperfections or the faulty arrangement is called as a defects. What is meant by defects? Defects means there is some faulty imperfections which are occurs in the crystal structure when the crystalline solids are formed. That means the real crystal is never a perfect crystal. There is some faulty or the imperfections in that crystal structure is occurs, and that imperfections or the faulty arrangement of the particle are called as defects. Then how these defects they are arises? Therefore, if the process of crystallization, is occurs at a faster rate than the required rate, if the process of crystallization is occurred at a faster rate than the required rate, then there is some imperfection, faulty arrangement of the particles of the crystalline structures are occurs. Why? Because when the crystal structures are formed, then during the crystallization, there is some faulty or imperfect arrangement. Why? Because when the crystal structure are formed, then during the crystallization process, if it occurs than the faster rate than the required rate, if the process of crystallization occurs faster than the required rate, then the constituent arrangement or the constituent particles are arranged irregularly. The constituent particles are arranged irregularly, due to which there is a faulty in the crystal structure, or there is a fault in the crystal structure, and that fault is called as defects. What are the defects? Again, I said you a definition of defects. When or if the process of crystallization occurs at a faster rate, then there is some irregularity in the arrangement of the particles which produces a fault in a crystal structure, and that fault is called as a defects. That fault which is produced during the crystallization process, because if the crystallization process is occur faster than the required आहे, त्यापेक्षा crystallization process ही खूप जास्त वेगाने झाली, त्यावेळेस at that time there is some irregularities in the arrangement of the particles which produces the fault, and that fault is called as a defects. So defects, they are having classified into three types. The defects, they are classified into the three types. So the defects are classified into following three main types. These are the classification of the defects. Defects means the imperfections. And why the defects occurs in a crystal structure? Because the rate of crystallization is faster than the required rate, and at that time there is some irregularities in the arrangement of the particles of the crystal structure, and therefore the faulty arrangement occurs in the crystal structure, and that are called as the defects. So this is the classification of the defects. Defects are classified into the three types. The first one is point defect, the second one is line defect, and third one is plane defect. The defects are classified into the three types. First one is here point defect, the second one is line defect, and the third one is plane defect. Further, the point defect are classified into the three types. The point defect are classified into the three types. The first one is Stysometric defect, the second one is non-Stysometric defect, and the third one is impurity defect. The point defect are further classified into Stysometric defect, non-Stysometric defect, and the impurity defect. Further, the Stysometric defect, non-Stysometric defect, and impurity defect are classified according to the stoichiometric defect are classified into the 4 types. Further, the stoichiometric defect are classified into the 4 types. The first one is vacancy defect. The second one is self-interstitial defect. The third one is Schottky defect, and the fourth one is Frankel defect. The point defect are classified into the stoichiometric defect, non-stoichiometric defect, and impurity defect. Further, the stoichiometric defect are classified into the vacancy defect, self-interstitial defect, Schottky defects, and Frankel defects. A non-stoichiometric point defect are classified into the 2 types. The first one is metal excess defect, and the second one is a metal deficient defect. Non-stoichiometric defect are classified into the metal excess defect and metal deficient defect. The third type of a point defect is impurity defect, and they are further classified into 2 types. First one is interstitial impurity defect. Interstitial impurity defect, and the second one is substitutional impurity defect. The second one is a substitutional impurity defect. So dear student, these are the classification of the defects in a metal crystals when a crystalline structure is formed. Defects are classified into the 3 main types, and out of these 3, in our topic solid state, we are going to study only the first type of defect is called as a point defect. The line defect and the plane defect, which is not included in our syllabus. In the defect, we are going to only the one type of defect is a point defect. And therefore, here we have seen the further classification of the point defect. The point defect are classified into the 3 types: stoichiometric defect, non-stoichiometric defect, and the impurity defect. Further, the stoichiometric defect are classified into the 4 types: vacancy defect, self-interstitial defect, Schottky defects, and Frankel defects. Non-stoichiometric defects are classified into the 2 types: metal excess defect and metal deficient defect. And here the impurity defect are classified into interstitial defect and a substitutional impurity defect. So this is the classification of the defects. That means in this topic we are going to study only the point defect. So only in this topic we are going to study the point defects only. So we are started with the point defects, and this is further so the point defects are further classified into the 3 types. Again, this stoichiometric are classified into the 4 types, non-stoichiometric are classified into the 2 types, and impurity defects are classified into the 2 types. But before going to start the classification of the point defects, first of all we have to see what is mean by point defect, and so that here we have considered a crystal structure. This is one of the crystal structure, and how the point defect is arises, and what is mean by point defect. And therefore a point defect is arises, this is a crystal structure, and a point defect is arises due to the fault in arrangement, of the constituent particles. This is the whole crystal structure, and a point defect is arises due to the fault in arrangement of the constituent particles. That means some constituent particles here, they are not present in the crystal structure. In the crystallization process, if the crystallization process occurs faster, then in the point defect, suppose this is the whole crystal structure and a point defect is arises due to the fault in arrangement of the constituent particles only. There is a fault in arrangement of the constituent particles because there is an irregularity in these crystal defects due to the point. Point means a particles. So what is mean by point defect? A point defect is occurs when, or it is arises when the crystal structure is formed, then there is a fault in the arrangement of the constituent particles only. Just I have compared the point defect with the second type of defect. In the classification we have classified the defects in the three types. The first one is a point defect and second one is a line defect. Then what is the difference between point defect and the line defect? In the point defect is arises or the occurs due to the fault in the arrangement of the particles. But in a line defect, suppose this is a crystal structure, and what is mean by line defect? In a line defect or the line defect is arises due to the missing of any one of the line, any one of the row, and therefore this is called as a line defect because there is a missing of one line, one row in this crystal structure. Suppose this is a whole crystal structure and a line is missing, whole one line, because this is the similar row arranged in the crystal structure. And point defect means only point, they are get irregular, they are get absent. But in the line defect, the whole line, whole row, it get absent. That is, there is a difference between point defect and the line defect. So in the point defect, there is only missing of the particles, or this is arises due to the fault in the arrangement of the particle, is called as a point defect. In the point defect, here we have to see the first type of a defect called as a Stysometric defect. And as we know, the Stysometric defects are classified into the four types. That means the Stysometric defects are classified into the four types: the vacancy defects, self-interstitial, Stysometric defects, Schottky defects, and Frankel defects. So what is mean by Stysometric defect? In a Stysometric defect, the stoichiometry of the solid crystal, it remains unchanged. In a Stysometric defect, the stoichiometry remains unchanged. That means the ratio of number of cations and the number of anions, it remains same, and it is represented by a chemical formula. In a stoichiometric defects, the ratio of number of atoms or number of cations and anions of the compound, it remains same. Stoichiometry means the number of atoms or the number of cations and anions, it remains same, and it is represented by a chemical formula. In the Stysometric defect, here first we have seen a vacancy defect. The first type of defect is called as a vacancy defect. And for the vacancy defect, consider these crystal structure. What is mean by vacancy defect? During the crystallization process of a solid, a particle is missing. A particle is missing from its regular site in the crystal structure. Vacancy defects means what? During the crystallization process, a particle is missing from its regular site, from its crystal structure. And the missing particles, suppose this is the crystal structure, and in a vacancy defects means during the crystallization, particles, they are missing. Here the particles, they are missing, and they create a vacancy. They lose their regular site because these are the sites of each and every particle in the crystal structure. In the vacancy defects, during the crystallization process, what happened? A particle is missing. A particle is missing from its regular site in the crystal lattice, and this missing particle creates a vacancy in the crystal structure. So these are the vacancies produces due to the missing of these particles from their regular site. These are some vacancies produced in the crystal structure. Why? In the crystallization process, during the crystallization process, the particles they miss their regular site and produces the vacancy, and therefore some of the lattice sites are vacant. These lattice sites they get vacant. Why they get vacant? Due to the missing of the particles from that site. And therefore there is a vacancy created or produced due to the missing of the particles from their regular site, and therefore the crystal structure is said to have a vacancy defect. So the crystal structure it produces the vacancy due to the missing of the particles from their regular site, and therefore this defect is called as a vacancy defect. And this defect is produced when that crystal structure when they get heated. When the crystal structure is or the substance means that crystal structure is heated, then the vacancy defect is arised. In the vacancy defect, due to the absence of particles, these particles they get absenced and create a vacancy, and therefore the mass of these crystal structure it get decreased, because the vacancy is produced in this crystal structure due to the absence of these particles, and therefore due to the absence of the particle the mass of the substance decreases. However, the volume it remains same. Volume does not changes, but the mass it gets changed, because here these two sides they become vacant, and therefore the mass of the crystal structure decreases, but the volume this remains as it is. This whole the volume is remained as it is, but the mass of the crystal structure or this is decreases, and therefore the density, as we know density is equal to mass upon volume. Here the mass it get decreases, the volume it remains unchanged, and therefore due to decreasing the mass the density of the vacancy defect or the density of the crystal structure in the vacancy defect it also get decreases. It also get decreases in the vacancy defects, and therefore as a result the density of the substance, this density of the crystal structure, that means a substance it get decreases. Why it get decreases? Because of the mass is decreases. And why the mass is decreases? Because of the particles they lose their regular position, regular site, and produces a vacancy. And therefore in the first type of first isometric defect, that means in the vacancy defects, here the mass decreases and therefore the density of the substance also it get decreases. So this is the first type of isometric defect is a vacancy defect. So what is mean by second type of defect is called as a self-interstitial defect, and for that consider a crystal structure. So here we have seen a second type of defect which what we call is as a self-interstitial defect, and for the self-interstitial defect again consider a crystal structure, a crystalline solid. So first of all we come to know about what is mean by self-interstitial or what is mean by interstitial sites. What is mean by interstitial sites? The interstitial sites of the crystal structures are the space or the void present in that crystal structure. So these are some interstitial sites. So the space available in the particles of the crystal structures they are called as interstitial sites. So these are the empty space available in the crystal structure, and that empty space are called as the interstitial sites. So the self-interstitial defect arises when the particle lose their position and goes into the interstitial site. They lose their position. They are present in that crystal structure, but they lose their regular position, their original position, and goes into the interstitial space or interstitial site. Interstitial sites means the void or the space present in between the crystal structure. So the self-interstitial defects, they occur in two ways. The self-interstitial, they occur in a two way. Firstly, when these are the particles, and during the crystallization, when these particles, they lose their regular site. They lose their regular site and goes into the interstitial site. They lose their regular site and they goes into the interstitial site. Therefore, here the two particles, suppose these are the two particles, these particles, they lose their original position and goes into that crystal structure but into the interstitial site, just like this. This is also one of the particle and goes into the interstitial site. So this defect is called as a self-interstitial defect. This defect is called as a self-interstitial defect. That means here a particle gets shifted from its original lattice point and it goes into the interstitial space in the crystal structure, and therefore here, because of the displacement of the particle, the vacancy is created. Here the vacancy, it is also created. Here the vacancy is also created, and therefore at the same time the interstitial defect arises, means they lose their original position and goes into the interstitial site, and therefore here also the vacancy is produced, but the particles, they are present in the same crystal structure, and therefore the volume remains same, the mass, it also remains same, and therefore the density for the self-interstitial defect, it does not get altered, it does not get changed, it remains as it is. It remains as it is. So this is the first way of a self-interstitial defect. Secondly, what happens? Secondly, suppose if we consider the crystal lattice here, this is one of the crystal lattice here, and in this crystal structure, here in this crystal structure, one extra particle, just like these points which are present in the crystal structure. Apart from that particle, one extra particle which is coming and it goes into the interstitial site. So these are two extra particles, but these extra particles, they are same, or they are the same as those already present in the crystal lattice. Means these particles same as that of these crystal lattice, but in this type of a same interstitial defects, the first type in which आता आपण अगोदर बघितलेला कुठला होता, सेल्फ इंटरस्टिशियल मध्ये तो त्याची रेग्युलर साइट सोडतो, दे लूज देयर रेग्युलर पोझिशन and goes into the interstitial site, and therefore vacancy is also created, but the particles are present in the same crystal structure and therefore the density remains unchanged. But second, in this second type of self-interstitial defects, new particles which is enter into the crystal structure, but that new particle is same as that already present in that crystal structure, and here an extra particles which is present in that structure, and therefore the total mass here, due to the particles which are new particles, extra particles are entering into the crystal structure and goes into the interstitial site, the mass, what happens with the mass? The mass of the whole crystal, it get increases. Density remains same. Density means this, volume means this is the volume of the crystal structure. It remains same, but the mass it get increases due to the addition of the extra particle into the interstitial site. The mass it get increases and hence the density also increases. So these are the two ways of the self-interstitial defect, one in which the original or the particle it leaves their original and goes into the interstitial site. At that interstitial effect, the density it remains unchanged, and for this type or in this type of self-interstitial only, the mass it get increases because the extra particle is added in the same crystal structure, and therefore the density also increases. So this is the second type of Stysometric point defect, is a self-interstitial defect. The third type of a defect is a Schottky defect. So for third type of a defect, which we call it as a Schottky defect, and for the Schottky defect, consider an ionic solid or consider an ionic crystal. In the type of a crystalline solid, we have seen the ionic crystals. Ionic crystals are the crystals which are formed from the ions. Ions means cations and anions. Therefore, in the Schottky defect, here we have considered ionic crystal, and in that ionic crystal, when there is a equal number of cation and anion are missing from their regular crystal structure. Here in a Schottky defect, for that consider this is an ionic solid or ionic crystal, and the Schottky defect is arises when there is a missing of one cation, and one anion. This is vacancy produced due to the anion, and this is the vacancy which is produced due to the cation. And when always consider that when we consider the ionic solid, in that when we draw the structure of cation and anion, as we know the anions are bigger in size than the cations. Always remember that. For the ionic solid, the cations are smaller than the anions, and therefore in an ionic solid, when equal number of cation and anions are missing, and they produces the anionic vacancy and the cationic vacancy, and therefore create a vacancy, and therefore it means that the vacancy created by the loss of one cation and one anion is accompanied. That means there is a loss of for one cation one anion. That means here the holes are created. Here holes are created, and always remember that here in this defect, such a pair of cation and anion vacancy defect. This is a vacancy defect, but here we consider the ionic solid, and in the vacancy defect we consider the crystal structure. Here we consider the ionic solid, and in this ionic solid, the vacancy is produced due to the cation and anion, due to the missing of cation and anion, and that vacancy is produced due to the anionic and cationic vacancy is called as a Schottky defects. Therefore, for each pair of missing or each there are two holes for ions lost, and therefore one is created by missing of anion and one is created by missing of cation. Therefore, a Schottky defect means here a pair of cation and anion. Pair means for one cation there is absence of one anion. म्हणजे जेव्हा आयोनिक क्रिस्टल मध्ये कॅटायन ऍब्सेंट असतो एक, तेव्हा एका कॅटायनला एक anion ऍब्सेंट असतो. एका कॅटायनला एक anion काय असतो ऍब्सेंट. and therefore the vacancy is produced due to the cation and anion, missing of cation and anion, and that vacancy of cation and anion is called as a Schottky defect. So what are the conditions for the formation of a Schottky defects? For the formation of a Schottky defects, here high degree of ionic characters are required. The first condition is high degree of ionic and cationic character are required. The second, the coordination number of anion is high. Coordination number means the number of neighboring sphere touching to that given sphere. Therefore, here for the formation of a Schottky defect, the coordination number of the anion it must be higher, and the small difference between the size of the cation and anion it will be required. The small difference between cation and anion it will be required. So these are the conditions for the formation of a Schottky defect. Schottky defect is also called as a vacancy of cation and ionic defects. So then what are the consequences? As the number of ions here, the number of ions it get decreases. Means ions means the particles from that ionic solid, cation and anion they are missing, and therefore the mass decreases. Here the vacancy is produced. Here the totally vacancy is produced due to the cation and anion, that means the pair of ions. The holes are produced and therefore the mass decreases, but the volume remains same. But the density of the ionic structure in the Schottky defect it get decreases due to the missing of cation and anion. But the neutrality, electrical neutrality of the ionic crystal structure it get maintained. Means what? Here in the Schottky defects, here the number of missing of cation and anions are equal in number. एक जर कॅटायन मिस झाला तर त्याला एकच anion मिस होतो. दोन कॅटायन मिस झाले, वॅकन्सी प्रोड्यूस झाली तर त्याला दोन anion काय होतात मिस होतात. and therefore electrical neutrality of the compound is maintained, it get preserved. For example, this defect means the Schottky defect is found in NaCl, KCl and AgBr crystal structure. This Schottky defect is found where there is a small difference between cation and anion, that means NaCl, KCl and in AgBr these defects is observed. So last type of a defect is called as a Frankel defect. And for the Frankel defect, here again we have considered the crystal structure. For the Frankel defects we have considered a crystal structure. So in that crystal structure, here we have considered the last defect is called as a Frankel defect. And for in this crystal structure, consider the Frankel defect arises when the ions in that ionic solid, ionic crystal, they lose their regular site and goes into interstitial site. And as we know, the cations are smaller than the anions, and therefore in the Frankel defects the ions, that means here the cations they lose their regular site position and goes into the interstitial site. Here the cations they lose their regular position and goes into the interstitial site. And why the cations only they lose their position out of the cation and anion? Because the cations are smaller in size than the anion, and therefore the finding of cation into the interstitial site is easy, and therefore a Frankel defect arises when the cation from these, therefore here the vacancy is produced. Here the vacancy is produced, and here there is no missing of the cation. There is no absence of the cation. The vacancy is produced due to the cation, but the cation in this crystal structure they goes into the interstitial site, and therefore Therefore, the Frankel defect, it is the combination of vacancy and the self-interstitial defect. It is the combination of vacancy and the self-interstitial defect. So, what are the conditions for the formation of the Frankel defect? The coordination number, it must be required a low. It required the low coordination number of the ions. Then the second one, the large difference between the size of a cation and anion. Because the cation, they lose their regular position, goes into the interstitial side. And therefore, it required the large difference between the size of the cation and an anion. So, these are the conditions for the formation of the Frankel defect. Then, what are the consequences here? Due to missing of cation, but they are not missed, they are present in the same crystal structure but into the interstitial side, the electrical neutrality of that ionic crystal structure, it get maintained. The electrical neutrality also get maintained. Then the second one, as there is a number of ion missing from the crystal lattice as a whole, the density of the solid, they does not remain same, because the cations are lose their position, they create a vacancy, but they are goes into the interstitial site of the same crystal structure. They are not get absent, just like the Schottky defect. In the Schottky defect, they are getting absent and create a vacancy. But in the Frankel defect here, they are lose their regular site and goes into the interstitial position, and therefore mass remains same, volume remains same, and therefore the density also remains same for the Frankel defect. So these are the four types of a Stysometric point defect: vacancy defect, self-interstitial defect, Schottky defect, and Frankel defect. So dear student, in this today's lecture, we are a defect, or we are done the defect in the crystal structure, types of defects, in that the types of a Stysometric point defect. These are the four types of a Stysometric point defect. So in this today's lecture, we will stop here. We will meet in the next module with the next point defect, that means a non-Stysometric point defect. Till then, thank you.